Before starting talking about electronic configuration for ions, let's review what are ions. Ions are atoms of the same element with different number of electrons. When you have your elements as they are in the periodic table, they are neutral. Neutral elements have the same number of protons and the same number of electrons. Your protons are positive charges. The electrons are negative charges. So if you have the same amount of positive and negative charges, they will cancel out. What happens when you have ions is that the number of protons is not changing, but the number of electrons will be different. You will have more or less electrons. So let's look at sodium here. I have sodium, my element 11, electron configuration for the neutral atom of sodium, right? With 11 protons and 11 electrons. You have 1s2, 2s2, 2p6, 3s1. So you have 11 electrons in total, and that's what you have in the electron configuration, 11 electrons. The total number of electrons for any element it's divided into two. We have core electrons, which are the inner electrons, and we have valence electrons. So everything that we're going to be doing from now on, it's based on the valence electrons. The valence electrons are the electrons that we have in the highest energy level. Remember, we have different energy levels where the orbitals are located, and we place the electrons in those different energy levels, specifically in the orbitals. So the highest energy level is the one that contains the valence electrons. Now, valence electrons are very important, and we focus on them instead of core electrons because valence electrons are responsible for the reactivity of the atom. The valence electrons can be transferred or they can be shared. When we say transfer, what that means is that electrons can be given up or an element can gain electrons. If an element is given up electrons or gains electrons, what you're getting is an ion. So an element losing electrons will have more protons than electrons, and it will have an overall charge that it's a positive number. An element that is gaining electrons will form negative ions. So you will have more electrons. If it's gaining, it will have more electrons than protons, and you will have an overall charge that it's a negative number. Now, looking again at the electron configuration for sodium, I have underlined the electron configuration using two different colors. In yellow, I have the 3s. And then everything else, it's underlined in that pink color. So you have the electrons in the first energy level and second energy level with a color, and then we have the electron in the third energy level in yellow. If you look at the different energy levels for that electron configuration for sodium, we have electrons in the first energy level, the 1s2, electrons in the second energy level, those two electrons in that s orbital in the second energy level, 2s2, and we have also p electrons in the second energy level, 2p6. Now, on the third energy level, we have the s orbital with one electron. Out of the three energy levels, 1, 2, and 3, first, second, and the third energy level. The third is the highest energy level. So that energy level, it's underlined in yellow because it's the highest energy level. And you have just one electron, this one right here. That electron, it's a valence electron for sodium. Valence electrons, electrons located in the highest energy level. For sodium, the highest energy level is the third one, and you have one electron. So that's one valence electron for sodium. We can actually assign the number of valence electrons using the periodic table. Sodium is in group 1 and it's going to have one valence electron. Looking at group number 2, electron configuration for sodium ends in 3s1. For magnesium in group 2, we are going to have 3s2. So for magnesium, we're going to have two valence electrons, but not just for magnesium. Everything in group 2 will have an electron configuration that ends in S2, okay? Depending on the period. For beryllium, you have 2s2. For calcium under magnesium, you will have 4s2. But everything is s2. So group 2 will have two valence electrons. When we move to the right side of the periodic table, we start with group 3 all the way to 8. And the group number, it's actually telling you how many valence electrons you have for each group. So you can predict the valence electrons for gallium. Gallium, it's in group 3 in the periodic table. It will have 3 valence electrons. Let's look at selenium. Group 6 in the periodic table, it will have 6 valence electrons. So you see how I wrote my group numbers here in yellow, because yellow represents the valence electrons, but it also represents the group number. So to determine how many valence electrons you have for an element using the periodic table, you don't have to write down the electron configuration. You can compare the electron configuration. You can look at the valence electrons from the electron configuration, but you can actually determine that number just by looking at the periodic table. Valence electrons, it's equal to the group number. Now, valence electrons for ions. Okay? Positive ions losing electrons, negative ions gaining electrons. So for sodium, we have the electron configuration 1s2, 2s2, 2p6, 3s1. Now, the ion of sodium is Na plus 1. The sign is telling you that it's losing. The number is telling you how many electrons it's losing. So the atom of sodium, neutral atom, with the same number of protons and electrons will have 11 protons, 11 electrons. Sodium plus 1, losing 1 electron, will have 11 protons. That number is not changing because that's your atomic number for sodium. But now, instead of having 11 electrons, if you have a charge of plus 1, losing 1 electron, the ion of sodium has 10 electrons. So we can write down now the electron configuration for Na plus 1. Na plus 1, 10 electrons. So we're writing an electron configuration for 10 electrons, not 11, because we have the ion with a charge of plus 1. One is 2, 2 is 2, 2p6, and we have 2 electrons, 4 electrons, plus 6, that's a total of 10 electrons. So let's write down the electron configuration for some ions. Starting with potassium. Potassium in the periodic table, it's element number 19. So if you have a neutral atom of potassium, you will have 19 protons, 19 electrons, right? The same number of protons and electrons, and it's given by your atomic number. When you have the ion of potassium with a charge of +1, a charge of +1 is telling you the positive that it's losing the number how many electrons. So potassium +1, it's the ion of potassium when your element, the neutral element, loses 1 electron. So your neutral atom of potassium losing 1 electron, instead of having 19, it will have 18 electrons. So what you're writing down is the electron configuration for 18 electrons instead of the electron configuration for 19. Whenever you're writing the electron configuration, you should make sure that the number that you're writing down for electrons matches the total number of electrons that you have. So I have 2 electrons here plus 2 here, that's 4, 10, 12 plus 6, 18 electrons. So the second one is calcium. Again, calcium, the neutral element calcium, has 20 electrons. Your atomic number is 20. You have 20 protons, 20 electrons. The charge of +2 is telling you that it's losing 2 electrons. So now you don't have 20 electrons. You will have a total of 18 electrons again. So you can write down the electron configuration for calcium +2 or the ion of calcium, and it will be exactly the same one that I have for the ion of potassium with a charge of +1. The third one will be aluminum +3. Aluminum +3, aluminum you have a atomic number equal to 13. If it's +3, it's losing 3 electrons, so you have now 10 electrons. At 10 electrons, you have to write down the electron configuration corresponding to 10 electrons instead of 13 because you have the ion of aluminum. So 1 is 2, 2 is 2, 2p6. We have to stop right there. That's 2, 4, and 6. That's 10 electrons. Next one, I have P minus 3. So phosphorus with a charge of -3, or the ion of phosphorus. So we check in the periodic table. P, it's element number 15. When you have the ion of P with the charge of -3, minus the negative sign indicates that that element is gaining electrons. The number, how many? So you go from 15 gaining 3, that will give you a total of 18 electrons again, which is the same electron configuration that I wrote for potassium +1, which is the same that you will have for calcium +2. And now we move to S minus 2. So S is element number 16. 16, when it's neutral, when you have the charge of -2, that one is gaining 2 electrons. So instead of 16, when you have the neutral atom as it is in the periodic table, 16 protons, 16 electrons, when you have the charge of -2, it will go from 16 to 18 electrons again, which is the same electron configuration that you have for potassium +1, calcium +2, phosphorus -3, 18 electrons. Cl -1. So checking Cl in the periodic table, it's element number 17. Neutral atom will have 17 protons, 17 electrons. This is the ion with a charge of -1, which means that your element is gaining, the atom for that element is gaining 1 electron. If it's gaining 1 electron, it's going from 17 to 18. One more, so I can explain new things in here. So nitrogen, the element nitrogen, it's element number 7 in the periodic table. Atomic number 7, neutral atom for nitrogen, has 7 protons, 7 electrons. When you have the ion of nitrogen with a charge of -3, it means that that atom of nitrogen gained 3 electrons. So it's going from 7 gaining 3 up to 10 electrons, which is the same electron configuration that I wrote for aluminum +3. 1s2, 2s2, 2p6. Now, if we check the periodic table with all of these ions that we have, we can actually see a pattern, and we can actually kind of predict the charges for different ions looking at the periodic table. You see, for all of them, we have 18 or 10 electrons, including sodium in the previous examples. And so for sodium, we have a charge of +1. It goes from 11 to 10 electrons. So we have 18 or 10 electrons. If we check the periodic table, element with 10 electrons or an electron configuration with 10 electrons is neon. An element with an electron configuration containing 18 electrons is argon. Both of them are in the group 8, your noble gases. Your noble gases, they have 8 valence electrons. They are in group 8, so they have 8 valence electrons. That's the maximum number of valence electrons that an element can have. All of them, not just neon and argon, everything below helium, not helium, neon, argon, krypton, will have an electron configuration that is s2p6. Neon, it's in period 2, so that will be 2s2, 2p6. Argon, it's in period 3, so that will be 3s2, 3p6. Krypton, it's in period 4, so that will be 4s2, 4p6. S2p6, they have 8 valence electrons. That's the last thing that you will have in your electron configuration for your noble gases. Every element in the periodic table wants to have 8 valence electrons. So your ions, the elements, are giving away electrons, gaining electrons, or what we're going to be learning in the future, sharing electrons. But regardless of what they're doing, gaining, losing, or sharing, it's always to have the same electron configuration as a noble gas. Noble gases, they have 8 valence electrons, which means that they are very stable. They have the maximum number. They don't want to give any of those electrons away. They don't want to get any electrons, additional electrons. So you see how potassium is going from 19 electrons with a charge of +1 to 18 to have the same electron configuration as argon. So the metals in the periodic table, they will lose electrons to have the same electron configuration as a noble gas. The non-metals in the periodic table, they will be gaining electrons to have the same electron configuration as a noble gas. Let's look at potassium. Noble gas, potassium is 19, so we have noble gas with 18 electrons. That's 1 electron less than what you have for potassium. And if you move further up to the front, like to the back, you have argon. Moving forward, you will have krypton with 36. If potassium wants to have the same electron configuration as a noble gas, right? The closest ones to potassium are argon, krypton. You can have also neon close to potassium with 10. For potassium to have the same electron configuration as neon, it will have to lose 9 electrons to go from 19 down to 10. For potassium to have the same electron configuration as krypton, it will have to go from 19 all the way to 36. So it will have to gain 17 electrons. You see where I'm going? To go to neon, same electron configuration as neon, it will have to lose 9 electrons, 19 down to 10. To have the same electron configuration as krypton, it will have to gain 17 electrons to go from 19 to 36. The easiest one is for potassium to lose just 1 electron to go from 19 down to 18 and have the same electron configuration as argon. Now I'm going to look at other elements in the periodic table. Let's check the ones that we have here. Let's check P. 15. We have 10 right here. We have 18 right here. For phosphorus to have the same electron configuration as neon, it will have to go down from 15 to 10. It will have to give away 5 electrons. For phosphorus to have the same electron configuration as argon, it will have to gain just 3 electrons. So phosphorus is a non-metal. Since they're close to the noble gases, close to group A, because your nonmetals are on the right side of the periodic table, it will be easier for the nonmetals to gain electrons than to give electrons away. It's easier for phosphorus to gain 3 electrons and get all the way to 18 than to lose 5 electrons to go all the way to 10. So that's why the nonmetals are forming negative ions. You see, I have phosphorus with a -3, I have sulfur with a -2, nitrogen -3, Cl -1. So nitrogen, it's element number 7. For nitrogen to have the same electron configuration as helium, it will have to lose 5 electrons. So it will be easier for nitrogen just to gain 3 to go from 7 to 10. Now, the charges that I'm giving you here for the ions, we can actually predict them using the periodic table. The number of valence electrons for group 1, it's 1 valence electron. So elements in group 1, remember the valence electrons are the ones that are being transferred. So giving away electrons, gaining electrons. If you have 1 valence electron in group 1, elements in group 1 can give away 1 valence electron. Something that is given away 1 electron will have a charge equal to +1, plus giving, and the 1, how many? Group 2, it's 2 valence electrons, right? So those elements in group 2 can give away 2 electrons. They are metals, and the metals will always be forming positive ions. So for group 2, we have charges equal to +2. Magnesium, the ion of magnesium has a charge equal to +2. The ion of calcium, right there in the list of ions that you have, a charge of +2. The ion of strontium right under calcium will form ions with a charge of +2. So ionic charges using the periodic table we have for group 1 +1, for group 2 +2. Now we move to the right side of the periodic table. You have aluminum right there, which is in group 3, and the ion of aluminum will have a charge of plus 3. Plus 3 because group 3 you have 3 valence electrons. When aluminum gives away those 3 electrons, will go down to 10, which is the same electron configuration as neon. So in group 3, I'm going to put in general a charge of plus 3. That applies for aluminum and gallium. And then we're going to move to the negative part. I'm going to skip group 4 and I will tell you why in a little bit. So you have nitrogen right there, phosphorus right there, and I gave you a charge for those ions, right? I'm giving you the charges here. Then we write down the electron configuration, and now we're relating that information with your periodic table. For nitrogen and phosphorus, we have a charge of -3, but not just for those two. That applies to everything in that group or family. So group 5 in the periodic table, they have 5 valence electrons. Okay? To go to a valence electrons, they need to gain 3. That's why they're forming ions with a charge of -3. Now we move to group 6. And group 6, you have 6 valence electrons. To go to 8 valence electrons, the same that you have for your noble gases, they will have to gain 2 electrons. So they will form ions with a charge of -2. In group 7, you have 7 valence electrons for those elements. For those electrons to have 8 valence electrons, they need to gain 1 electron. So they will form ions with a charge equal to -1. Now, group 4, we're not going to assign a charge using the periodic table for group 4. I'm going to give you just one example. If you check carbon, atomic number for carbon is 6. So for carbon to have the same electron configuration as, let's say, helium, noble gas atomic number 2. Right? So for carbon to have the same electron configuration as helium, it will have to go from 6 to 2 electrons, which means that it will have to lose 4 electrons. 6 losing 4, that will give you 2, which is the same number of electrons that you have for helium. But carbon with 6 electrons, right? If you look at neon, 10 electrons. For carbon to have the same electron configuration as neon, it will have to gain 4 electrons. So it's the same number of electrons to go to the same electron configuration as helium or neon. So in this case, since it can be one or the other because it's the same, you can think about this as the same amount of energy. Same amount of energy, it's related to losing 4 or gaining 4. Since it's the same, we cannot predict a specific charge using the periodic table. For the other main groups, 1, 2, 3, 5, 6, and 7, in general, the ions will have the charges that I'm writing here, but not for group 4. We can determine the actual charge for an element in group 4 when it's in a compound, and that's something that we do in the future. Now, looking at transition metals and how the electron configuration for transition metals is going to work. We have our notation for the fourth and the fifth period, which are the ones that we need to know. Fourth period, argon for H2, 3dx. And remember that X is the number of electrons that you have in those d orbitals for transition metals. So iron is element number 26 in the periodic table. So you have 26 electrons. So we can write down the electron configuration using our notation right there. This will be argon. And since the atomic number for iron is 26, I'm going to write down my atomic number right there, 26. I have 18 here for argon plus 2, that's 20, which means that in my d orbitals, I'm going to have 6 electrons. That will add up to 26. Remember, you need a total of 26. So this is 18, 2, and 6. That's your 26 electrons. Now, when we're writing the electron configuration for iron plus 2, and I'm going to write down that one right here. Iron plus 2. For iron, you have 26 electrons. When you have iron plus 2, you don't have 26 electrons. Iron, the atom of iron, neutral, the neutral atom of iron will have 26 electrons. But your iron plus 2 means that it's losing 2 electrons. So now you don't have 26, you will have 24 electrons. That's the total number of electrons for iron plus 2. So it's losing 2 electrons. That electron configuration that I just wrote, it contains 24 electrons, right? You have 18 electrons right here for argon. That's 2. And this is 4. And that will add up to 24 electrons. But that electron configuration is not correct. Valence electrons are the ones that are being transferred. Valence electrons are the electrons that you have in the highest energy level. If you look at your electron configuration for iron, no charge, the neutral one, you have argon 4s2 3d6. Your s electrons are in the fourth energy level. That will be the highest energy level, the fourth one. 3d orbitals. Your d orbitals are always in a lower energy level. So your electrons in the s orbital are in the fourth energy level, which is the highest one. So when iron plus 2, it's losing 2, when iron it's losing 2 electrons to become iron plus 2. The 2 electrons that iron is losing are the electrons in your fourth energy level, which is the highest one. So you have 18 electrons and then you have 6 electrons, and that will give you 24 electrons. That is the same as having argon 3d6, also 24 electrons. So when your transition metals are losing electrons to form your ions, and it's always losing because they're metals, and the metals are always losing or giving electrons away. Transition metals will always lose the s electrons first because the s electrons are always in a higher energy level than the d electrons. When you're writing the electron configuration for iron plus 3, now we go down to 23 electrons. We have 26, losing 3 will go down to 23. The first 2 electrons are being removed from the 4th energy level, which is the highest one. And then to go down to 23, we're going to have 3d5. That's 18 electrons plus 5 electrons. That gives you 23 electrons. So now try to write down the electron configuration for zirconium and zirconium plus 4. This is a summary of all the information that we can get from the periodic table. So for the basic part of the periodic table, we have the periodic table, right, divided into these 3 main groups. Big groups, we have the metals, the metalloids, and the non-metals. We have all the metals on the left side, no color for those. And then we have the inner transition metals right here in 2 different shades of purple. Those are still metals. Now highlighted in pink we have the metalloids. Highlighted in green we have the non-metals on the right side of the periodic table. So that was the first thing that we learned about the periodic table. We have groups and we have periods. Groups are your vertical columns, and they are also called families. The elements in the same group, they share similar chemical properties, similar physical properties. So we have your groups, main groups going from 1 through 8, right? No numbers for the transition metal. Your main groups are group 1, 2, 3, 4, 5, 6, 7, and 8. You have names for group 1 and group 2. You need to know the name for those groups. And you have names for group 7 and group 8. So you also need to know the names for those 2 groups. So make sure that you make a note in there with that information. So we have the periodic table. We can use the periodic table to determine the electron configuration for the elements. S block is what we have on the left side, where you have group 1 and group 2. Then we have P block on the right side, where we start with boron all the way to your noble gases, not helium, because you don't have P6 for helium. That applies from neon down. So helium is just 1s2. So that's your P block on the right side of the periodic table. And then we have the D block right in the middle, right? Where you have your transition metals, D1 all the way to D10. Valence electrons are given by the group numbers. So you have your main groups numbered from 1 all the way to 8. In yellow, that's your group number, which is also giving you the number of valence electrons. And in addition to that, in addition to like determining how many valence electrons you have for the elements just by looking at the periodic table, we can also assign a charge for the ions of the elements using the periodic table. Main groups, again, you have your group 1. All of those elements in group 1 will form ions with charges equal to +1. Groups, group 2, all of the elements in group 2 will form ions with charge of +2. We move to the right side, we have +3 for group 3, and then we have negative for group 5, 6, and 7, -3, -2, -1. Remember that hydrogen is placed in your group 1 because it shares similar properties with the alkali metals, but hydrogen is a gas. So hydrogen also shares some properties with the noble gases all the way on the right side of the periodic table. Now helium is your first noble gas, atomic number 2, but helium has an electron configuration related to what you have in your group 2. See how group 2 ends in S2, and you will have the same thing for helium, S2. Now we can also assign valence electrons for the transition elements. Not using the periodic table directly, but looking at the electron configuration. So for the fourth and fifth period, and this should be 5s2 for the, you see how you have for the fourth period you have 2 electrons right there. That's the highest energy level, the fourth one with 2 electrons. In the electron configuration for the fifth period, you have 5s2, and the 5 is the highest energy level. So you have 2 electrons in that s orbital. Since the d electrons are always in a lower energy level, all of your transition metals will have 2 valence electrons. Those 2 valence electrons are the 2 electrons that you have in the s orbital. The d electrons are always in a lower energy level. And one last thing very quickly, transition metals, they are transition metals because they have electrons in your d orbitals. And one of the main differences between transition metals and the metals from the main groups is that your transition metals can form ions with multiple charges. For example, you have iron. Iron can form ions with a charge of +2 or a charge of +3. Copper can form ions with a charge of +1 or a charge of +2. But there are transition elements that they will always have the same charge, like silver, Ag, always ions with a charge of +1. Zinc and cadmium, even though they are transition elements or transition metals, they will always form ions with a charge equals to +2.